Hi, good morning. So we'll start the class now. You can see 45 has joined it. Okay, so before the class starts, I'll make two announcements. First is we now have that course uh, adjustment is done. So we'll make the group now. Okay, so what I'll suggest is you make a group of five person by this Sunday. Okay, and then I'll share a Excel sheet after this class and you just update there. You make your group, and so this group is for two purposes. One purpose is we'll give some project on high level synthesis. We'll give detail on that. So you have to work on that high level synthesis project, and also I'm going to give a research topic related to this high level synthesis and serious VLSI, and you need to read certain things. Certain things will be assigned, certain things you have to explore, and then you have to make a presentation on that. Okay, so this is what two things are needed for this group. So you make your group by this Sunday, and group will consist of 5%. The second announcement is that we have the exam one on 9th February, that is in the next Tuesday. Okay, and it will be using MS forms. Question will be MCQ, MSQ, and short answer type, but it is in rapid fire mode. Okay, so we'll give more questions, and the time to solve will be less, right? So the essentially you also now get familiar with this online platform, and the purpose is something just to make sure that you concentrate on your solution instead of helping your student, right? um, Although I don't know whether it will be fully proof or plagiarism proof or not, but that is not something I can control always in this mode. But I'll try to make sure that you have very less time to help your friend, okay, rather than helping yourself. Okay, so yeah, so announcement. Hmm. Yeah, any question on this?
The quiz will be during regular class timing.
Yes, yes, it will be in the class time only. So during this 11 to say 12 to 1, but the exam will be mostly for say half an hour, not more than that. So I'll announce all these things, exact timing and all those things. But it will be using MS Forms and in Teams only, and in the class hub. Okay, I think
Sir,
done.
what will be the syllabus up until?
Whatever will be taught till this week, till tomorrow. Okay.
Okay, sir.
So till Tuesday, so Friday I won't take classes because Friday and Monday there will be no class. I'll be out of station. So whatever I'll taught till tomorrow will be the syllabus. Uh, okay. So let's start today's class. So we are. Let me share the screen. Is my screen visible?
Yes, sir.
So so far we have basically discussing various scheduling strategy, right? So initially we saw about this ASAP and ALAP, which is basically unconstant. ALAP is not exactly unconstant because there is a latency constant, but ASAP is unconstant, and then we move to this ILP based formulation, and we basically categorize the scheduling problem in two things: two dual problem, MLRC or MRLC. And then we saw that ILP formulation of both for MLRC and MRLC, and then we moved for a generic or a special class of scheduling problem where all are multiprocessor, all your function units are multiprocessors, and all operations are unit delay, and the graph is DAG, and then we saw Hughes algorithm for that, and we saw how to calculate lower bound for that and all. And then we basically take the idea from the Hughes algorithm, and then we move to a list-based algorithm. List-based algorithm, which is basically heuristic algorithm, is basically does not ensure the optimal solution, but we can argue that they always give, they most of the time they give good solutions. Okay. And in the last class we have basically discussed one of the one of the strategy, which is basically minimization of the latency under resource constraint. That means your resource constraint is given and you try to do a list based scheduling to minimize the latency, right? And what is the basic intuition of this list scheduling is you maintain a list, right? List according to the priority of the operations. So you have to define a priority of the nodes of your graph, and then you basically and then for each resource type you basically have a priority list, and you take the highest priority node and you try to schedule it, right? So your decision will be taken based on the highest priority node, right? So for list scheduling, this priority is important, and we have seen this that path length from the sync node, right, is something, is a good measure of the priority. So the node which has more value, the more distance from the sync node is actually has a highest priority, and that actually satisfy the data dependency constraint as well. So if you just schedule the operations based on this priority, it also satisfy the data dependency constraint, because I mean we have already discussed that schedule should be valid. That means it's, if there is a dependency between two operations from vi to vj, the vi must be scheduled first followed by vj, right? So this ordering actually makes sure that the precedence constraint or the determinacy constraint is followed, right? And what we have seen, the idea is basically, if since this is a generic type of solution, operation can be multi-cycle, and operation type can be different, right? So we identify two things. So if some operations which actually started, so we are talking about scheduling in say time step L, and we are actually in time step L, and then we try to find out which are the operations which is basically available to schedule in this time step, right? What does it mean? Its predecessor has started early enough so that it finished before L. So its predecessor node actually completed his execution so that this node is available to schedule. It is called ready list, right? So ULK is the ready list. So these operations ready to be scheduled. And since the operations are multi-cycle, we identify another terminology called TLK. If some operations started early but still continuing, right? And these are the basically most critical nodes. They have to allocate some resource in this time step also, because they have already started and I cannot stop them in between, right? So these are the kind of critical operations that has to be scheduled in the time step. After scheduling this operation, if some resource available, I can schedule some operations from the ready list based on their priority. Okay? That's the overall idea. And we have seen the algorithm is basically for each resource type. So we identify the ready list, the operation to be scheduled in the time step L. So I am starting from time step 1. So time step 1, 2, and so on. So I'm actually increasing the time step every time. So I'm basically this one of this inside for loop will consider one of the time step, right, for each type of resource. So what I'm doing is basically every time I identify the ready list, I identify the operation that is actually running on that particular time step. So I'm only identifying a subset of the ready list, which after allocating the node that are critical, right? So I'm actually allocating resource for this first, and then I'm selecting a subset of the ready operations so that it actually satisfies the resource bound, because this is basically ML minimization of latency under resource constraint. So resource constraint is given, so that AK is already given for each type of resource, right? So, and we argued in the last class that this selection will be based on the priority, and priority is basically the longer the distance from the sync node. Okay. So this we have already discussed in the last class, and we have shown that if we just take this particular graph or DFFQ example, and then say if you take resource bound is 3 and 1, and multiply delay is 2 and ALU delay is 1. So then how it should work? So in the first time step, when I'm in the time step 1, for resource type multiplier, there are 4 operations are actually available, right? So we already know this thing, that there are 4 operations are in the ready list in the U1K, 1 1, K is 1, right? And then So now, and I have given 3 multipliers, so I have to select these 3. So I'm going to take only those 3 node which has the distance high value, right? So we know that the distance of this node is 4, this is also 4, and this is 3, and this is 2. So I'm going to take this 1, 2, and 6, right? That is what I have done here. So I have done that these 3, and they will continue till second step. And for ALU, only one operation is available here. The rest of the ALU operation is not available in the ready list. Only one node in the ready list, and I have only one ALU, so I'm going to schedule that also in time step 1. Right? That is my time step 1. So now when you are in time step 2, my all 3 multiplier, because I have 3 multiplier available, all 3 are occupied. So although there is in the ready list I have one multiplier, in the ready list I have this 8, but I cannot schedule it here because all my 3 multiplier is occupied. So that means this TLKT L is basically time step 2, and say K is 1 for multiplier, it is already 3, and my A1 is also 3, right? So it means that I do not have any extra free resource which I can use for the ready list. In the ready list I have V8, right? So in the time step 2 I'm not going to schedule any multiplication operation, but since this is done, so in the ready list for ALU operation this is already there, and I can schedule it in the time step 2 because this finishes execution in the time step 1 because it's the delay is 1. Okay, so similarly, so this is the only operation scheduled in the time step for resource type 2. And then in the next time step, once these 3 operations is done, my ready list consists of 3, 7, and 8. So there are 3 multiplier in the ready list. There is no operation is running. The T3 1 is 0. So I'm going to schedule all these 3 in the time step 3. Right. So this is what I'm going to do. And then for ALU, I don't have any operation, so I cannot do anything. In time step 4, all multiplier are occupied, so I cannot allocate any, and there is no multiplier in the ready list, and I have to continue this. And there is my ALU list for also is ready list is also empty because there is no operation free at this 2 time step. So ALU will be remain free for this 2 time step, right? There is no operation to be done. Then in time step 5, all multiplier are done, so all 3 multiplier will be remain idle for this 3 cycle because I have 6 multiplication operation. They are all done by time step 4, right? And then I basically start my things at time step 5, and then in the time step 5 I have in my ready list for ALU I have only one operation. So, and I can schedule it here. In time step 6 I have only one operation to one operation is there. Sorry, I mean I'm so in time step 5 I have 2 operation to in the free list, right? So I'm sorry. So there are 2 operation to be scheduled, but this distance is 2, this is 1, so I'm going to select this one. So I have selected only this one. In time step 6 I have 2 operation in the ready list, right? 5 and 9. So both have delay distance is 1, so I can select any of them. So I have scheduled 5. I could have done this one also here, right? And in the time step 7 I have only 9 in the free list, and I just schedule that 9 in the time step 7. So I need 7 time steps to schedule these operations in using 3 multiplier and 1 ALU with the delay of the multiplication is 2 unit. Okay, so this I mean this we have already discussed in the last class, and I hope you understand that. So
Sir,
now, yes,
excuse me.
please.
Sir, ready list means the like whenever this thing resource is free, then it becomes the operation becomes under ready list, or if the operation can be performed at that time instant, it will come in the ready list. Like which way it is called ready list, sir?
Is something whose predecessors has done, is completed his execution, and I can schedule that particular operation in the time step.
Okay,
And
sir.
he is the critical list which is running, right? So ongoing operation, so which is basically must to be scheduled, right? And ready list is something whose predecessors are already completed his execution prior to my current time step. So that means this operation is now ready to be scheduled. Okay.
Sir, and in the last 3 timestamps, like how do we give the order for this thing? Like we could give whatever way we order that is, we could either give it as how to say 9, 4, 5 also we could give, or 4, 5, 9 also we could give. Both doesn't like changes the timestamp, right? So like the final latency, right?
Yeah,
So
it
how
is
do
true,
you
but yeah, it is true. But at time step 6, what are the operations available? 4 and 9, right?
yeah,
And now when there are two operations is ready to be scheduled, and I have only one ALU left. So what I'm going to do, I will take the priority, the node which has highest priority. So the priority that I have fixed is basically the distance from the sync node. So the node 4 has priority 2 and node 9 has the priority 1. Okay. So I'm going to select 4. So in time step 5, I have no other choice. I have to schedule 4. I cannot schedule 9. Although they all give me the same schedule, because only one, there are 3 operations left and only one ALU. So I need 3 time step. But according to the logic, at time step 5, I should not schedule 9 because 4 has the better priority or the higher priority than 9. Okay.
okay.
In time step 9, now 5 and 9 are both are available. Both have priority 1. So I can schedule either 5 or 9. So I have shown here the solution with 5, but you could have put 9 here and 5 here. So both are same. But time step 5, I have only one choice. Because by the algorithm, right? Um, because 4 has the higher priority than 9. Okay.
Okay, sir.
Yeah. So now the question is, now I want to do the other problem, right? So the other problem is basically minimization of resource under latency constant. Now the problem here is that so I have given my latency. So suppose in this case, let us assume that all operations are single cycle, and I have given say 4, or say I have given 7, right? So I have given 7, and I have assumed that multiplier has delay 2 and ALU is delay 1. But I don't know they have 3 or 3 1 or 2 2 or 3 2, whatever that is, I don't know. So now I have given this particular graph, and I have given you the number 7. So I told you that you schedule this behavior in set 7 time step, and you are using the minimum number of resource, right? How the resource, how you should write, your this how do you find out the minimum resource for that? So you understand the problem, right? So in the reverse problem, the dual problem, here the resource bound is given, so you can take a call here, right? In time step 1, I have 4 operations to be scheduled, and I know because I have 3 multiplier, I can only choose these 3 operations, right? But the reverse problem is little bit difficult, right? Difficult in the sense there is no bound given for resource. Rather I have given the bound for the latency. So so basically the problem is even same, right? When you are in time step 1, you have this 4 multiplier to be scheduled, right? So 1, 2, 6 and 8, and you don't know how many multipliers are there. So whether you're going to schedule 1, 2, 3 or 4, it's something you have to take a call there, because you are going to schedule the operation in time step 1, then 2 and 3, 4 and so on, right? Only thing is given that you have a 7 time step. You have to do everything by 7 time step. So how we get the resource bound? Because in the first problem which I just solved, the resource bound is given 3. So although there are 4, I am going to select 3 by multiplier which has the highest priority, right? So here how can we go ahead? So anybody has any idea? You understand the problem, right? So in the first problem which we just solved, the resource bound is given, right? So resource bound is given, my AK is given. So now this AK is not there. So this is something a question mark. I don't know. This is what I have to figure it out. So how we are going to do this here? So since it's a list scheduling, the steps will be something like similar, that you have a ready list, you have TK, some operation is unfinished, and you have to select a subset of this UK, the ready list, right? But problem here is that how do you choose this subset, because AK is not given to you. Only things I have given some lambda, that this is the maximum time you can take. So then how you can actually reframe the list scheduling algorithm? So anybody has any idea? This is how we should do.
So can we go bottom up like in ALAP?
So ALAP, if you go by ALAP does not guarantee the minimum resource, right? It's just make sure that whatever the latency is there, it will just meet that. You remember, right? Because if say to take the same example here, so in the ALAP I am going to schedule this operation, this operations, this all 4 operations, right? So it does not guarantee the, you understand, right? So if you do a ALAP on this, 5, 7, 9 and 11 will be scheduled in last time step, right? Whatever the time step is, because these operations are available to schedule because his sync node is already scheduled. But our objective is to minimize resource, right? So just going by blindly by ALAP won't solve the problem.
Should we
Anybody
find
else?
should we
Yeah.
find mobility of the each process or each operation, then like try to space it so that like minimum resource, like in a particular timestamp there are minimum operations, and we are able to finish the in like minimum latency possible.
Yes. Yeah, I think he is very close, not exact. I mean, not, although it is not something exactly the solution that I'm going to discuss in a minute, but he is very close. So, although, so the argument that I'm going to place here is, although this AK is not known to me, but so if I know certain operations of SK, which is basically critical for this time step, whose mobility is very kind of zero in the current time step, right? So they have to schedule. If I do not schedule them there, I'm going to that means I'm not able to schedule the rest of the things within the minimum latency which is given to me, right? So the idea here is that, so I'm going to start the whole process assuming that I have only one multiplier and one ALE, right? So I'm assuming that this is the minimum possible, right? So this is the minimum possible, and in a particular timestamp, if I found there are some critical operations which mobility is kind of zero, which has to be scheduled in the timestamp, so I have to increase the resource to schedule them, right? And once I increase the thing, obviously I cannot reduce it further, right? So that means once I increase, I am going to use that particular number of resource for the rest of the schedule. Okay, so let me just explain the thing, and there are a lot of pros and cons here. I'm going to discuss them. So, for example, here, so I have given a latency. This is what is that algorithm that I'm talking about: minimization of resource under latency constant. Right. So my latency bound is given lambda, and the sequence graph is given. So I assume that I have all resources basically 1. So this is a vector. A is a vector, basically vector of all resources. And then you identify the latest possible start time, the ALAP time for all the node based on this lambda, because you know that for ALAP you need the latency bound, otherwise you cannot start from last, right? So you need to know this is 7 times step or 4 times step or 5 steps. So now if you see that if your T0, that means the source node schedule become less than 0, that means this is, you cannot schedule this particular behavior within the time limit given, right? So the lambda given. So we'll say ki there is no solution possible. Otherwise, solution is possible, right? So if this T0 is greater than equal to 0, it means, when ideally it should be exactly 0, then it is the minimum lambda given to me. If it is not, I mean, it is greater than 0, that means I have given some buffer of latency. Okay. But ideally, for minimum lambda given, the T0 should come out as 0. Okay. So this is something I just have a pre-check whether my latency bound is sufficient to execute the behavior in that timestamp or not. Right? So that's all. Then what I'm doing here is, so I start with my timestamp, same thing, because list scheduling is always like that. You take a timestamp, you take a resource, you identify the ready list, you identify the running operation, the TK, and then you basically schedule operation based on the priority, right? So that's all. So what I'm doing here, so for each resource type, say for each resource type, I identify the ready list. Right? So I identify what is the operations which can be done, and then I compute the slack. Slack means in the current timestamp. So what is basically the TLAP, the latest possible schedule versus the current timestamp. So if it is the last possible value, then it will come as a slack 0, right? So So if you go back to this example, so in say in the time step 1, if I just consider this multiplier, so if I consider this multiplier, so there are 4 multiplier, and then I know the slack for this node will be, because if you say assume this is a, now I am not taking this particular solution, say I have given lambda equal to 4, right? And this assume that all operations are single cycle. You can always extend the things for multi-cycle. So I know these are the 4 operations are ready to be scheduled, and so in L equal to 1, since the distance of this node is 4 4, so their slack is 4 minus 4 is kind of 0, right? So they are basically critical operation, and it is slack is 1, its slack is 2. So what does it mean? So there are 2 operations which is basically critical to be scheduled in this time step. Okay, so although I have assumed initially that I have only 1 multiplier available, but I found there are 2 critical operation or 2 operation which is critical to be scheduled here. So I need at least some more resource to do that. So I'm going to increase my resource count. This is how I'm going to go conservative way, right? So what I'm doing here is I identify the operations to be scheduled, ready to be scheduled. I identify their slack. Slack is basically the current timestamp. So the ALAP value is TALAP. That means it is the last possible schedule versus my current time. This is the difference between that. And so for all those such operation in the ready list, this is my priority now. This is my priority. It's not the distance. Rather, this slack is my priority, right? And I identify the operations which is with a 0 slack, and I have to schedule them. The example that I just showed, I have actually 2 operations in the time step 1, which is basically 0 slack. So although I assume that I have 1 multiplier, I'm going to update this. So initially it is 1 1. I will now increase to 2 1. Right? So I am assuming the first one is the multiplier and the second one is the ALU. So to make sure that, so suppose I am explaining again with a single cycle operation and lambda equal to 4, right? Which is basically very known to us. Since there are 2 operations which is basically 0 slack in timestamp 1, I cannot make sure that this particular operation to be scheduled in 4 timestamp using 1 multiplier. So I just increase the multiplier bound from 1 to 2, and I am just scheduling 1 and 2 in the timestamp. So you can actually enhance this line to take care of the TLK also, right? So that something is missing here, but you should actually think about the modified version of the algorithm where there are some running operations also, right? But the idea here is that the priority actually changed from the distance to slack, and I'm going to consider the operation which is a 0 slack in a particular timestamp. If there is a 0 slack operation which cannot be scheduled using the number of resource available, I have to increase the resource to accommodate this operation in that particular timestamp. So this is I'm going to do for every timestamp. Okay, and then whenever my sync node is done, I'm going to stop it. Okay. So let me explain here. So let's say I have again I consider the unit delay in the single cycle, and my minimum latency is 4. Right? This is something we know. This is the minimum possible for this example for single cycle. So what is going to happen here? So in the ready list, in the first time step, I already told you there are 4 operations, and so their TLAP value is something you know. This is for this it is 1. This is also 1. Because this is how you do, and for this is TLAP value is 2, for this TLAP value is 3, right? So if you start with this, so now if you in timestamp 1, so this 1 minus 1 is 0, so for that slack will become 0, for that slack will become 0, for this slack will become 1, for this slack will become 2. So I need to increase the multiplier from 1 to 2, and I'm going to schedule these 2 operations definitely in timestamp 1. Okay, so that is what I'm going to do. And for ALU, I have only one operation whose so since only one operations and one ALU, I don't care about the slack or anything. I'm going to schedule it here because I have one resource available. So in timestamp 1, I'm going to schedule 2 multiplier and 1 ALU operation. In timestamp 2, now I have these 3 operations to be scheduled, right? So I have these 3 operations to be scheduled. It's basically ready to be scheduled. And now for this, now I have my L equal to 2. So his ALAP time is basically 3. sorry 2, because ALAP time is 2 and your timestamp is 2, so his criticality become 2 minus 2 equal to 0. So for this node, now criticality become is basically it is now L. So if you just calculate this algorithm, so the TLAP minus this. So for this node, it was 2 minus 2. Again, it is become 0. So 2 minus 2 equal to 0. And for this node, because it is sorry, not for this node, it is 2 minus 2 equal to 0. I'm sorry, 2 minus 2 equal to 0, because this is already scheduled. And for this node, 3 is the TLAP value, and this is timestamp 2. Now for this node, it will become 1. So I found the node 2 and 6 is basically now critical. They have to schedule in this timestamp. Okay. So, and this node has still buffer 1. So it is not still 0. So it is have some buffer. So what I'm going to do is I'm going to select 3 and 6 and I'm going to place them in timestamp 2. I'll delay operation still 8 because it is still not become critical in timestamp 2. And for ALU operations, I have only one ALU available. I mean, one operation to be ready, and I'm going to schedule it. And in timestamp 3, now this 7 and 8, these two are basically there. And now since 6 is also done, so 7 and 8. So for this also the TLAP value is 3, and in now I'm timestamp 3, so the slack becomes 0 now. For this node also TLAP value is 3. I am now in current timestamp 3, so their slack also becomes 0. So I have to schedule 3 and 8 in timestamp 3, and I have 2 resources. I don't have to increase the resource bound. So basically, sorry, 7 and 8 is going to be scheduled in timestamp 3. And for ALU, I have only one operation to be is ready, so I'm going to schedule it here. And then in next timestamp, it is now important. So in the next timestamp, there is no multiplier, everything is done. Now for ALU, the 9 is available and 5 is available. So I am in timestamp 4 now, and and this is his TLAP value is 4. We can know that because this is the last node, right? So then 4 minus 4 equal to 0. So his slack becomes 0. And for this node also TLAP value is 4 because this can just schedule in the last timestamp. And I am in timestamp L equal to 4, so it also becomes 0. So there are 2 ALU operations which become critical now for the timestamp 4, and I have only one ALU. So I cannot do these things in 4 timestamp using one ALU. So I'm going to increase the resource bound from 1 to 2 in timestamp 4 to accommodate 5 and 9 here. So I have scheduled 5 and 9 2 ALU operations in timestamp 4 by increasing the ALU bound. So which is basically now the final bound become 2 and 2. So that is what is the minimum resource needed for this graph. So obviously this is the minimum solution because this is a tree. But if this is not a tree, you may not always get this good solution. So I hope you understand the point here, right? Any question?
Excuse me, sir.
Yeah.
So whenever there is a minimum like maximum latency is given as the like minimum possible one, so ALAP will be the solution always. Is it like that?
Can you repeat your question?
That is like here we know that 4 is the like minimum possible latency. We can't achieve less than 4 latency in this given
Yes.
circuit. So in generally, whenever there is when the condition like latency constraint is given as minimum latency, minimum possible latency, ALAP will be the solution always to achieve
it is
minimum resource.
No, basically what I'm saying is ALAP is not, so ASAP. So ASAP is something give you the lowest bound. So your ASAP will give you the lambda value, and then you can utilize that lambda to just check by ALAP whether it's a feasible or not. Did you understand? ALAP does not give you any minimum bound. It's basically given a lambda. It just may tell whether it is possible to schedule all the operation within the lambda bound or not, but it does not calculate that. Right. So
no, ALAP, I'm saying in terms of the diagram, like if you see the previous diagram, it is similar to the one which we derived it in ALAP, right? Like ALAP, we were trying to schedule the.
No. If you do ALAP for this graph, 5, 9, and 11, all these 3 will be scheduled in last timestamp. See here, I have
11.
not scheduled 11. 11 also going to schedule in the last time, right? So, but it is not here. So it is not exactly the ALAP, right? And if you go by this, I can tell you in the timestamp 3, so for 10 will also come here, because 11 will be come here and 10 will come here, right?
Okay. Okay. Sir.
And in multi, and then yeah, so whenever his successor is done, it is going to be, this is not ALAP solution, right? So you, because I am actually going in a conservative manner on the resource available.
Okay. Okay. Sir. Yeah. Thanks.
Excuse me,
Yeah.
sir.
Yeah, please.
Sir, like I was thinking of an algorithm like using binary search to improve on the complexity. Like we can keep take a low and high for the each resource and then use a binary search taking the middle value and see if it's possible to do it in lambda or not use with that particular count for the resource. And
So for this particular algorithm, complexity is order of n, right? So I hope you understand that, because it is just taking the node one at a time, right? So it's basically order of n. It is some constant time factor of n, right? So how your solution? So here, I mean, before answering your question, I'll tell you one interesting thing here. Say, for example, I force to increase the resource bound at only timestamp 4 for this, right? Because at the timestamp 4 only the ALU become not sufficient, right? So I need more operations. I mean, more operation become critical, and I force to increase the ALU bound at the timestamp 4 only. Okay. So now the interesting thing here is that now in the actual hardware, this particular ALU is available from timestamp 1. It is not that it will come and jump into the hardware in timestamp 4, right? So we've identified there are 2 ALU needed. So now, I mean, I could have actually do some rescheduling, right? So that, because so that since the one ALU is idle here, one ALU will remain idle here, that particular ALU will remain idle there, right? So probably I could have accommodate this operation here itself now. So that is also a solution, right? But that is something I have not done. So what I'm trying to mean is that you can actually do some kind of readjustment, because I came to not only timestamp 4, where that I need at least 2 ALU to do all these things in 4 timestamp. Otherwise, I cannot meet the time bound. But that particular ALU remain idle for the rest of the thing, and I can see that in some cases, say for example, this 9 could have been done. I mean, in this particular example, probably it's not, but probably in some cases, some kind of flexibility will come, right? So that something is not um, is something this ALU solves this list scheduling, but something you could have have a different schedule with, if you know that this 2 and 2 is the available resource from timestamp 1, right? So you could have end up in a different schedule also. That is something I want to make a point. Yeah, now you can please give your question again.
so can you go back to the previous slide?
Yeah.
So like I was thinking like for each resource type you are we can within the each resource type we can have a binary search type algorithm where we fix the number of the resource and then see if it's possible to do it in lambda and accordingly update. But like now I understand like the complexity will actually increase, we don't need to do that with given.
Yeah, and you may not end up getting the best solution. And the basic idea of this list scheduling is it does not get, although in this example, because it is a tree, list scheduling always give you the best solution, as you have already seen for use algorithm. But yeah, please.
So like in the previous example, like initially we are fixing the time steps and then we are deciding how, like we are calculating how many resources we need, right?
So what I'm doing here is that I'm not fixing the timestamp. I am actually identifying I am actually starting from the timestamp 1, right? And then I identify the operation which basically become critical in that timestamp, right? So if some operation become critical in the sense, if I do not schedule them in that timestamp, I cannot meet my lambda, the target latency.
Yeah, I mean, yeah, you're fixing the lambda, right? So
Yeah.
like after fixing the lambda, you're doing this. So my doubt is like until in the last time step 4, because we need 2 ALUs and we only have 1 ALU, we have decided to increase on the ALU, and like we have decided then okay, we need to increase the number of resources we have because
Yes.
it's not possible. But so at the end you are saying to do this we need 1 multiplied and 2 ALUs. But from
No,
the time
two
step,
multiplier, because at the timestamp 1 itself I decided
that's
that
right.
1 multiplier is not sufficient. Yeah.
Yeah, so but like you have added the ALU in the last time step, right, sir? But if
Yes.
we know that we have an extra ALU from the starting itself, then the scheduling can be different, right? In a different example, maybe.
Yeah. For this example, it is not, but that is what I just make a point, right? So if I know that my resource bound is 2 from timestamp, probably I can take a better call, right? Better decision, and which may not end up. I mean, we may end up in a less number of latency, but probably that might give you better resource allocation in terms of say registers or interconnection, right? I'll discuss those things in the next classes, because based on your schedule, uh, your number of register requirement is different, number of interconnection marks, demultiplexer, multiplexer, switch is different, right? So probably if I know this 2 at the start state, I could have go for a different solution or a different schedule, which may not reduce the number of timestamp to schedule, but it may reduce the number of register required or the interconnection cost, right? So that something is there, but that is not how this algorithm there. But you can always do another run, right? So now you can just run this complete algorithm, because it's very fast, it's order of n. You can just assume that my whole thing is 2 right? And then you do a schedule again, just you pass the whole algorithm 2 times, you will get another solution, right? So where basically you try to you know that 2 is the minimum bound, and let's reschedule, right, the behavior so that which may end up having a better resource utilization in terms of interconnections and register, not in terms of the FUs. Okay.
Okay.
Sir, just once again, sir, coming back to binary search, sir, I think it will perform actually better. Sir, just listen to my algorithm once. Let's say
Sure.
we take we take low to be 1 and high to be say 10 power 9, and every time we take the mid, so let's say we come to mid, let's say I, and we check whether it is possible to schedule it in lambda or not using I of that particular resource type. If it's possible, then we'll reduce high to mid -1 and see if it's possible with a lower value. If it's not possible, we'll increment low to mid +1 and try to get the answer from the higher value. So this way at the start only we'll know the mid value, right? So at start only we can keep scheduling, like keep using those many resources from the beginning only, and even if that is not possible, then we obviously have to try with more resources. So the correctness I think will be ensured, and complexity we won't
Yeah,
have to.
so what I'm trying to understand for your answer is, so are you doing this binary search at before start of any scheduling, or in every timestamp you're going to do?
I won't iterate over timestamp. I won't need to iterate over timestamp, right? Because all I have to do is I'll have to check whether using these many resources I can schedule it in lambda or not. I have the mid number of resources in the beginning
No, but
only, right?
how do you know? How do you know which? I mean, because see, there are 7 multiplier here, right? So sorry, 6. There are 6 multiplication operation here, right?
Yes, sir.
So from this 6, how do you know that? I mean, 5 is sufficient or 2 is sufficient,
So
right? So
let's say I
how
start my mid value is, let's say, 3. So I have 3 multipliers. So
Hmm.
I'll schedule them greedily, right? I'll schedule the first 3 multiplications in the first, and the remain then the next one in the second, based on the dependency. So
Yeah.
that way, if I'm able to finish within lambda,
Hmm.
I know that mid value is sufficient. Maybe less, we can do it in less, but I know we can do it in 3. So that
Hmm.
way I'll update my high, and so this way I'll traverse like log in n log n
So
basically.
you try to mean that you will basically, so basically there will be another outer loop here, right? So you
Yes,
try
sir.
to mean here is that, yeah.
Instead
So
of
basically
leaving
yeah, I think what you try to mean is this, that there will be another outer loop here. Sorry. Yeah, so basically there will be another outer loop here, right? So which is basically go from this their binary search, right?
Yes, sir.
So
But
you
then we
start with
won't need
10 and you say with 10 you identify that you can actually schedule everything in say 5 times 10 in 3 times 10, say for example. Then you basically since you have more buffer in the latency, you reduce the things and you try to do that. Right? That is
yes.
something you okay. So here, say suppose you, but I feel the problem with this algorithm, what you say you start with say 10, right? So with 10, you probably meet. So if you do this, because it has that particular example, you have uh, 4, that critical path length is 4, so you need at least 4 timestamps. So even if you take 10, you will get a solution, right, in 4 timestamps. So your lambda will be 4 only, right? L will become 4. So then you, but 8 of them is unused, right? So how do you basically, so basically if you go by that way, you need at least basically 3, because there are 3 multiplications operation are there. So probably if you take, so this all 4 is going to be scheduled there, right? So you may end up having a decision that I need at least 4 multiplier.
No,
What I'm
sir.
trying to say is your binary search, if it meets that L become lambda, right? So your L become lambda after
Yes.
this inner loop. Then you may end up use more resources. It does not guarantee that that is the minimum resource available.
No,
So
sir,
I'll tell you.
I won't stop when L becomes lambda. I'll stop only when L becomes lambda minus one. Like even if I
Yeah,
am able to do it in lambda, I'll still reduce. Like check even if it's possible with two to do it in lambda. I know that with three it is possible to do it in lambda. So I'll check if even with two it is possible to.
I think that your logic is something other way. So if say you meet 4, then you still again reduce, say from 10 to 5. You again run, you
Yes,
again
sir.
meet 4, you are done. So then you make it 2, and then so your L become 5. So that means with 2 it is not possible. So I'm going to take the previous solution as the current solution, something like that.
Yes,
Right?
yes,
That
exactly, sir.
probably will work. Yeah, so that probably will work. But again, since you are going by binary search, so from 5 you will become 2. So if 2 does not give you a solution, you will go by 5. Why not 3?
No,
Right?
no,
So again,
sir.
you have to probably increase.
I won't go to. I won't just stop when it does not work with
I
two. I'll
understand. So you basically have to again search from 2 to 5. That
yes,
range, right? Whether
exactly.
it's a 3 or 4. Yeah. Yeah.
Yes,
So
sir.
that something is also, but complexity will be more, right? So there's some n log n, because that binary search will be top of this order of n algorithm.
Sir,
Right?
but here you are also traversing L. The lambda part is also there in the complexity. That won't be there. Here the complexity is n into lambda, right? Because L is traversing from one to like.
Yeah. Okay.
So that way n log n would be less than the
It is
complexity of.
L plus N basically, right? So either you schedule a operation in L or you go. It is not L into N. It is L plus N, right? In my algorithm.
Oh, okay, sir. Okay, okay.
Yeah. So yeah, I mean, whatever you are suggesting. What's your name? I could not see you people. That is the problem. What's your name?
Sram Udbhav.
Yeah. So yeah, this is maybe another yeah. Whatever he's suggesting is whatever I'm doing. In top of that, there should be some binary. I take some upper limit and range, and then he'll do some kind of binary search to end up having the minimum resource. And which has the advantage. What he is trying to say that, because here I already claimed that I only came to know about this upper limit of ALU is 2, but I'm going to only utilize that in this timestamp. I cannot use this in this timestamp because I don't know about that. But in his algorithm, at the start itself, he knows this is 2 2. So he can actually utilize this 2 2 from start 1 and probably end up having a better schedule. Yeah, that is something is probably is another way of doing the things. Yeah. Okay. Good that you come up with something. Okay. So any other question?
Excuse me, sir.
Yeah.
Sir, like if in the question they have given the maximum latency to be 5, like here it is given 4. Like if it is 5, will our solution method will be able to reach or 2, 1, like 2 multiplies and 1 ALU, like will it be able to reach that solution?
Yeah, yeah. So obviously, right. So if it is given 5, yeah, actually it's a good question. So basically, what he is asking is that. So I know the 4 is the minimum here, so that's why I need. So we get 2 2. But if you think this, if is the 5 is given, eventually it will go by the same schedule. Let us try to see if this is 5. So let me just try to answer his question. So say suppose it's 5. So what will happen? So this is ALAP time is ALAP time will be 4, right? So ALAP time will be 4, and in sorry, ALAP time will be sorry. This is 5. This is 4. This is 3. This is 2. Sorry, ALAP time will be 2, and in current, so it has a buffer 1, right? It has buffer 1. It has buffer 2. The slack is basically 2. This is 3. So in the timestamp 1, if I start with 1 1, I am going to schedule one of them, only one. I am going to postpone this here. You understand my point, right?
Yes, sir. Yeah.
So this is basically the ALAP time minus current timestamp. So ALAP time, if you take lambda equal to 5, this will be 5. This is 4. This is also 5. The ALAP time I'm writing here, right? So this is 4.
Sir,
This
but
is
won't
4.
you schedule 10 also right now? Like 10 because ALU is free right now. So you won't you schedule 10 also right now?
No. So basically, what I'm going to, I mean, the things will start from timestamp 1, right? So not the other way. So in the timestamp 1, there are 4 multiplier available to schedule. So I'm going to calculate their slack value, right? So since it is ALAP value 2 and I am in L timestamp L, so 2 minus 1 is 1. So this also basically 2 minus 1 is 1. So for this, let me just write down the ALAP value. This is 4 and this is 3. So 3 minus 1 is 2. For this node, the ALAP value is 2, and it is sorry 5 4 sorry, and 4 minus 1 is 3. So there are 4 multiplier, and none of them is basically 0 slack. So none of them is critical. So what I'm going to do, I'm going to only schedule one of these two guys, right? So only I'm going to schedule say 1. So 2 won't be there. You understand my point?
Yes, sir.
Yeah. So you end up having a different schedule, but you can actually do this as a homework, and you may identify how many multiplier and how many ALU is needed. And probably you still need 2 ALU, because I mean my apprehension is that it will basically, so maybe whatever the solution Udbhav says, maybe a better solution, because you end up having again 2 because what will happen, because this multiplier will be delayed by 1, that means this will be delayed by 1, right? So this operation will be delayed by 1, this operation will be delayed by 1. So at the end of the day, what probably will happen, this 5 and 9 will come in the last time step, right? So then we have no choice other than taking 2 ALU. Right? I'm not sure, but you can actually cross check whether you get 2 1 or 2 2.
Sir,
Yes.
but like in the previous solution, we saw that we are increasing, like our ALU count increases at times at 4 from 1 to 2. So here in this question, if I'm giving as 5, the ALU can be 1, because instead of timestamp 4 one ALU operation, timestamp 5 another ALU operation we could schedule. So it should be 2 comma 1 as the optimum solution, right? So could we arrive at that solution?
But if you take 5, your other timestamp will change. It's not, you will not get this exact solution. That is the point I'm trying to make. So if you take the 5 timestamp, right, instead of lambda equal to 5, instead of 4, you will not going to schedule 1 and 2 in timestamp, only one of them in the timestamp 1, because none of them becomes 0 slack. So this schedule, rest of the schedule won't be same. This will change. So once you come here, you may not have only 5 and 9 and you are in timestamp 4. So then you are going to delay this here, right? Then it is fine. But what I'm trying to make the point is that since it's a heuristic solution and since you have a buffer of 5 1, so in that your schedule for timestamp 1 and 2 and 3 will change.
Sir, but we are supposed to get minimum resource according to this algorithm, right? So
no, yeah. So now it is a heuristic. You try to understand this is a heuristic. So it so for 3, yeah, for 3 it will give you yeah. I mean, if it is, so basically for this particular example, it will give you 2 1. You can solve it. I mean, I cannot. I mean, you can actually let's solve it now. So what's the problem? So let's try to solve it now. So I start with, so I'm going to schedule 1 here, right? So I'm going to schedule say 1 here. So there is no small space here, right? So
one more doubt, small doubt here.
Yeah.
Here in this case, you're allotting at the timestamp 1, you are taking 1 multiplier, right? Another, like we have assumed start with 1 ALU already. So can we allot 10 or 10 operation 10 also in the first timestamp? Because
Yeah,
we are
yeah,
having
obviously. Since one is available, I'm going to allot one. So I'm not going to say, I'm not going to keep the ALU free. If you go the algorithm, I'm going to make sure that so if you have say resource bound is given, I'm not schedule operation not needing additional resources. I'm going to schedule always them, right? So that means the number of resource available, I'm going to always allot operation there. But if there is zero slack, I'm going to add resource. So in that case, if I start with 1 I'm going to schedule 1 and 10 in timestamp 1. In timestamp 2, now this 2 become critical. So I'm going to schedule 2 and say only 2 become critical. I'm going to schedule 2 only here. And in timestamp 3, now this 3 and 6 both become critical. So I'm going to schedule 3 and 6 here. And in timestamp 4, this 8 also will become critical. 8 and 7 will also become critical. So I'm going to assign this 4 and 7, 7 and 8, 7 and 8 in the timestamp 4. And ALU also will be same way, right? So since 3 is scheduled in timestamp 3, and I can do this 4 in timestamp 4, right? So eventually I can feel that you end up having two multiplier and 1 adder. So you will get minimum solution because this is a tree. Understood? Hello?
yeah, just a minute, sir. I'm just
Hello, sir. In the meantime, I had a doubt. So,
Yeah.
in OPHUB's approach, in which we were using binary search, we have multiple types of resources, right? So, we will have to apply the binary search for each of that type of resource. So, it won't really be that straightforward, and the complexity will be a lot more than the current algorithm that we are following. So, could
Yeah,
you please?
it is actually correct. So whatever you are saying is correct, because if you just have say the bound for this multiplier and so basically we do not write the algorithm finally, right? So what I'm trying to just see, he is suggesting something that can we know some bound at the start and do the scheduling, right? So his suggestion was that you just do binary search, but whether the binary search for only one type of resource now and the other time second time, or we'll do in parallel, that's something you can always come up with something. And this is a heuristic. We can always come up with something that may not always guarantee the best solution, but if it is working fine for most of the cases, then it is allowed, right? See, heuristic, you cannot say this is wrong, and because it does not guarantee the minimum schedule or minimum minimization, right? Because in some cases it may end up having more resources. Okay, so as long as it's basically give a valid schedule, is a correct algorithm because it's a heuristic.
Okay, sir. Thank you.
So does it clear your doubt? Who was asking the question?
sir. Yeah, it was me.
Yeah.
So could you show here, like according to we were going right. So according to the algorithm, the operation 9, like operation 9 would be sorry, not operation 8 would have been scheduled at timestamp 4, right? Like if we consider the case latency. So operation 8 would have been scheduled at timestamp 4, and operation 7 also would have been scheduled at timestamp 4, right? So if 7 is at timestamp 4 and 8 is also at timestamp 4, so in the timestamp 5 we will be again needing to
5 and 9. So yeah.
So again we are coming to a conclusion of 2, 2, right? So
Yeah.
how do we
You are
rectify
saying
this?
that probably if we start this 1 and 2 in timestamp 1, probably we end up having So
But
it's a
so
good.
I think according to the binary search, like that his algorithm, the other fellow mate was saying, if we follow his, maybe we could arrive the solution, right?
Yeah. So basically, I also basically identify the problem, right? Because you take a late call, and by that time you cannot utilize that things early, right? So that means this particular algorithm, whatever I just discussed in the class, may not be the good one, and you can have a better version of that by just taking some upper bound, or say, in my opinion, is something is better is you do this. you take a two pass of the algorithm, right? So in first pass you identify this limit and then you start reschedule the things from start, so which will basically probably give better, but again that won't give you 2-1 in this example, whatever you are trying to point it out here. So yeah, it's a something good good discussion today. But again, what I'm trying to mean is you can have a better heuristic than this, right? So which I mean, either maybe binary search or something. But if you know some bound at the start, probably you can take a call. And as he mentioned here, that the problem here is that since these two are interdependent, I mean this 5 and 9 depends on this operation 7 and 8, right? And I'm not considering that aspect here, because I'm not considering this 7 and 8 during scheduling of 7 and 8, whether that will impact 5 or 9 or not, right? So something they are upper bound of resources, because if I just schedule this 8 somewhere early or say 7 somewhere early, then probably I can manage with one ALU, right? And I know that this particular uh, uh, so in for 5 time step, it is possible to schedule the things using 2 multiplier and one adder. If you just check this particular diagram, you can actually end up having a 2 multiplier and one adder or one ALU for 5 latency solution, right? So that means in that case, this algorithm does not perform better. It does not give you the minimum value, and you can have a different heuristic which probably meets your purpose. Okay.
Can a
Yeah.
small last, can this be a solution, that is the at the like whatever timestamp we are finding that we need to increase the resource, shall we again start the loop from the start, that is considering this as the like we like start with a1, like consider like at timestamp 3 we recognize that 2 multipliers are needed, so again we'll start from timestamp 1 with a1 as 2 or a2 as 1. So
yeah, it is I think a good suggestion that whenever you increase the resource, you go back to timestamp 1, you restart from time, you make L equal to 1, and again you start from 0, right? So whenever you're, I think it is something a very good suggestion that you start with 1 and then if you have 5 only in timestamp 3, you are forced to schedule 2, you have to increase the multiplier. So let's go back to timestamp 1 and you start doing things again. So then probably then 1 and 2 will be scheduled there, and then his problem will be solved, right? So that may be work much better in most of the cases.
but the time complexity increases, right? At that case, I'm not
Yeah,
able to
so
calculate.
as long as it does not become n square or something, say with say some extra resources, still it is a some yeah. So it is not significantly increased, then probably it is okay.
It will become worst case n into lambda, right? We at every timestamp we might have to start from the
Yeah.
beginning.
So instead of lambda plus n, it is n into lambda, which is something I guess it's not that huge. Obviously, I mean, objective of the heuristic algorithm is to make the things running fast, right? So as long as something uh, as long as it's not a significantly increase but give a good performance benefit, probably you can go for that. It's basically a kind of a choice whether you are okay with just making it lambda into n, right? In my opinion, which is something is not that significant improvement of in the complexity, whereas you will get more good benefit of utilizing those resources from start one, right? So it's basically a design choice, but the solution that you come up with, I mean, I feel that is much better, because you can, whenever you feel there is more resource, you go back and reschedule the things utilizing that too. Okay, I think you understand the basic concept, right? So any other question? Otherwise, we'll conclude the class. I think